Welcome to Lesson 8 of Lower Fifth Atomic Structure, all about nuclear fission. So, nuclear fission is the splitting of a large unstable atom's nucleus into two smaller nuclei, and this release of 2 or 3 neutrons plus gamma rays. So this large amount of energy is released by the fission reaction. So there are 2 types of nuclear fission: induced and spontaneous. So induced fission occurs when an electron is absorbed by uranium-235 nucleus or the plutonium-239 nucleus, and the nucleus splits. Or spontaneous fission, which is rare and occurs without a neutron being absorbed. So let's have a look at nuclear fission. Here's nuclear fission. A neutron is fired into a uranium atom, and this is very big. And the fission emits 2 daughter nuclei, 2 smaller nuclei, which are, in this case, krypton and beryllium, and 3 neutrons. And then each of these 3 neutrons can hit into another uranium atom and split that. And so energy is released when uranium nuclei are split into 2 smaller nuclei during nuclear fission. And in the reaction above, a neutron from a previous decay can lead to more and more decays, and this is called a chain reaction. And this is the main way we get energy from, or get nuclear energy. So again, here's one of these chain reactions, where 1 neutron goes in, it makes some smaller nuclei and some neutrons, which then go into the bigger ones, which then go and produce smaller ones and more neutrons, and so on and so on. And so if a neutron is released in the first fission and it collides with another uranium nuclei, more fissions will occur, resulting in a long chain reaction. But the sad thing about this is this could go out of control, and this is what happened in, for example, Chernobyl, Fukushima, and even in atomic bombs, if we want them. So, a chain reaction occurs when neutrons released from each fission event cause further fission events to occur. So you've got the neutron, hits into the larger uranium nuclei, which splits into some daughter nuclei and makes some neutrons, which then again, in turn, hit into uranium-35. So, what can fission? So mainly, enriched uranium-235 and 238, but uranium-38 is non-fissionable. And enriched means 2 to 3% of uranium-235, which is a lot considering naturally there's less than 1% of it. So uranium-238 doesn't undergo fission, but absorbs neutrons, becoming plutonium-239, and plutonium-239 is fissionable, but not in a uranium reactor. So, in power plants, uranium-235 or plutonium-239 atoms decay and give out energy and neutrons. Each time a uranium atom splits, it produces 2 to 3 neutrons. And these neutrons can go on to hit other uranium or plutonium atoms, which causes them to split and causes a chain reaction where more and more energy is released. So here's the nuclear power plant. So the fission reaction takes place in the reactor, and here's the reactor, where the coolant is heated, and the coolant is pumped into a boiler and boils water to make steam. This is a very common way to produce energy, and it's the same way we produce energy with fossil fuels. And the steam then turns the turbines, which rotates the generator to produce electricity. And then this transformer steps up the voltage so it can be transmitted to homes via wires. And this then goes to the national grid, which is already seen. So, here's a nuclear reactor. And inside this nuclear reactor, we have several things. We have fuel rods, we have a graphite core, we have control rods, and a coolant. So, we're going to have a look at what each of these 4 things are. So, the fission reaction takes place in a nuclear reactor, and it needs to be controlled. So the control rods absorb the fission neutrons to ensure that, on average, only 1 neutron per fission goes on to produce further fission, which controls the energy. So essentially, this is a way in which we have more and more, or we have the same amount of energy produced over time. If we want more energy, we will absorb less neutrons via the control rods, and if we want less energy, we'll absorb more neutrons in the control rods. So the fast neutrons don't cause further fission. So in a reactor core, a moderator is used to slow the high-speed neutrons down, and water or carbon dioxide can both act as a moderator and a coolant. So, what do each of these things do? The fuel rods contain the uranium isotopes that split when triggered by an incoming neutron. The graphite core acts as a moderator, and this slows the neutrons down so they are more likely to be absorbed into a nearby fuel rod. Control rods raise and lower to stop neutrons from travelling between the fuel rods, and there's a change in speed of a chain reaction. The coolant is heated up by the energy released from a fission reaction and is used to boil the water to drive the turbines in the power station. And a concrete shield absorbs all the harmful ionizing radiation given out by the radioactive products of the fission, again protecting all the people working in the plant. So, inside the reactor, plutonium-239 and uranium-235 undergo fission in the nuclear reactor, and the reaction is controlled by moderator and control rods. So, in comes a fast neutron that gets slowed down by the graphite moderator. This hits into the uranium nuclei, fission occurs, producing two smaller daughter nuclei and three neutrons, which again hit into the uranium nuclei, fission occurs, but this time the control rods absorb two of the fission reactions neutrons, so only 3 neutrons are produced again and are let through. So here 3 neutrons went into the nuclei, and here 3 are. So this will mean the same amount of energy is going to be produced. Finally, what are nuclear bombs? In the nuclear bomb, there's uncontrolled chain reactions. So they don't have moderators, nor do they have control rods. And they just want fission to occur as fast as it can, causing the bomb to explode and release a load of energy.